Okay, it's 5:25, I believe, and let's get started. So, a few announcements. pset3 is out. There are some really, really cool problems, and I think it's slightly easier than problem set 2, so hopefully that'll be a nice benefit for that one. Any questions about pset3? So there are two cool problems. One of them is about computational biology and this thing called edit distance, and you'll basically be showing that a version of edit distance is context-free, and the other one, which is how small could you make a grammar for a specific language? So that'll be pretty interesting. pset2. Any questions about pset2? Yeah.
So when you say W reverse, do you mean that we should flip the beats or we should come to the back?
I don't know what the first part was.
If W is 0, 1, for instance, so W reverse would be 1, 0?
Yes. Yeah, it's just the reversal of the characters.
From the back.
Yeah, so if it's W1 through Wn, the reverse is W1 to W1. Yeah. Yeah.
Is it enough to give a counterexample, or do you want us to explicitly use the pumping lemma?
Well, in order to use pumping lemma, you have to give a specific example of a language.
Let me see if I can if you're able to figure out that it's a regular language, something.
Yeah, so just say this is a regular language, and you can either say this is a DFA, or it's, for example, if it's even length strings over the alphabet, for example, then say we've seen that this is regular, pretty much.
Okay, cool.
Yeah. Any other questions about pset2? So I was thinking of extending it to the deadline to Thursday, but I looked at pset1 and I counted the number of I don't know submissions. Anyone want to guess on how many I don't know submissions there were on pset? 50? It wasn't that high. It was like a third, almost exactly a third. So
like completely everything's I don't know.
like of all the question submissions, which is 85 times 5 for the non-bonus one, 33%, 0.5% of them were I don't know submissions. So if you want to give me an argument as to why I should extend it to Thursday, I'm happy to hear. Yeah.
Good students should be punished for bad students.
That actually is legitimate. Yeah.
What if you tell us to put something like on the top right corner,
but that'd be in the video, so yeah.
You don't know. You can just not tell what it is. Just like draw it on the border. Don't tell anybody what it is.
Yeah.
Extending it to Thursday would allow us to go to office hours twice before the deadline to ask questions.
Right.
That'll be enough. So I'm extending this to Thursday.
Thank you.
My pleasure. I expect these to be a lot better.
The problems are more straightforward.
What's that?
The problems are very straightforward.
In pset2 or 3?
The two.
Yeah, I figured that they were somewhat straightforward. There are little tricks in a few of them, but they're mostly straightforward. Other questions about pset2? So pset3's deadline will stay the same, but pset2 I'll put Thursday. I'll make all the changes tonight. Any other questions before we get back? Okay, so what were we talking about last time? Yeah, Pushdown Automata. So we had this machine model called a Pushdown Automaton, which is essentially just an NFA, but now we can use a stack. And we can do operations such as push or pop, or neither or both, all those possibilities. So what were we talking about with Pushdown Automata last time? What did we actually start doing? Or did we want to show? Yeah, we were able to convert a arbitrary CFG into a PDA. So what were we attempting to accomplish by doing that? It showed that the languages accepted by CFGs and PDAs are the same. And we did one direction, so every context-free language is recognized by a PDA. And then now, what do you think the other direction is? Yeah, convert an arbitrary PDA to a CFG. So that's what we're going to talk about for the first half, hopefully. Well, you may think, well, we can do something like the regular grammar to NFA process where the reverse was almost exactly identical to the forward direction. And let's think about if that would actually work here. Remember when we converted an arbitrary CFG to a PDA, we had those 4 base states, the start state which pushed on a special symbol, then we pushed on the start variable, the looping state that handled all of the rules, pushing them on in reverse order, all that stuff. And then at the very end, we had this transition that popped off that special symbol to a final state where we could accept. But of course, not all PDAs are the same. Do we have to push a symbol on the first transition of a PDA? No. What about an NFA where we converted it to a PDA by saying we never touch the stack, you never pop or push on any transition? Is that a PDA? Yeah, I just don't do anything to the stack. So that already is a PDA. So none of those transitions will ever pop or push. So we don't necessarily have the same structure if we want to just do the process in reverse. So we do have to think about this in more detail. So the questions I put on Piazza, the most recent one, are actually going to be really helpful here. So I'm going to ask a few questions. Can any PDA be converted into one that has exactly one final state? So this is almost the same question where I asked about NFAs before, but now I'm asking about PDAs. Could we do that? Yeah, so how would I do that here?
Say all current final states, do a triple epsilon transition to a new final state.
Exactly. Perfect. So if I have, let's say, 2 final states without loss of generality, then I'm going to make a new final state in a different color. And I'm going to have transitions to it from all previously final states. So I'm going to make those non-final. And then I'm going to have the triple epsilon transition to them. Okay, so that's good. We can convert any PDA into one that has exactly one final state. Well, let's see. How did the CFG to PDA process work when we did it the other way? Well, what we did is we pushed on symbols to correspond to a derivation in the grammar. Well, the pushing of the symbols here or popping of the symbols may not necessarily correspond to anything corresponding to the input. So what could we do?
Sorry.
You need a longer cord.
Oh.
All right. So that's nice that we were able to have a single final state, but we're going to need another tool here. So can any PDA be converted into one that on every transition either pushes or pops, but not both or neither? So just to reiterate what the question is, can I convert any PDA into one such that every transition does exactly one of push or pop? But so it doesn't do both push and pop, and it doesn't do neither or pop on any transition. Well, let's see. Let's look at the 4 cases. So I'm going to make a little chart here corresponding to the 4 possibilities. So here's a handy table. Well, if it pushes but doesn't pop, I don't think I need to modify that transition because it already does exactly one of them. So that entry is good. If it doesn't push and it does pop, that's also a valid transition according to this question. So I'm going to say that that's okay too. But now we have these 2 boxes where it either does both or neither, because we may have, in an arbitrary PDA, I might have both of those transitions. So can I fill these 2 entries? So let's say we're trying to fill in doesn't push, doesn't pop. Could I replace that transition with maybe more transitions that do exactly one or of both of them? Yeah, how would I do that? So what I do is, if we have a transition like this, so let's just say that we're reading A, it doesn't matter what A is, and we're doing neither push or pop. So go to Q prime. We're going to convert this into 2 transitions. So I'm going to have Q and Q prime same states. But I'm going to insert a brand new state Q double prime. And so what should the transitions be between these states? Yeah, does it matter what I push the first time? No, but does it matter what I pop on the second one? It has to be the same one because I want to have the exact same stack contents from when I started at Q and ended at Q prime.
This is kind of a silly question, but could you do it the other way as long as you like push the thing back?
Great question. Could I do pop first, then push?
The same thing.
Yeah, I could do that. It is possible, but should I do that? No, why not?
It's not sufficient.
The stack might be empty, and I might end up with an empty stack. So so the logic is sound, but except for the possibility of an empty stack. And since I said that the PDA may never push a symbol, I can't guarantee that the stack may not be empty. So we're going to have that the first transition is going to it's going to push some symbol. Then the second transition is going to pop the exact same symbol. But it doesn't matter what I push because it's going to go away anyway. And the first transition or the second transition is going to read, it doesn't matter which one reads, as long as one of them reads the symbol A, or whatever A is. So here we're going to push on, let's say, an X, and we're going to pop an X on the second transition and push nothing. And so now those 2 transitions have exactly one of push or pop. So that's great. So we now have handled the no case. Yeah. Oh, thank you. I like to think that I insert these on purpose to see if people know. That was totally my mistake. Okay, yeah, you're correct. You read an A on one of them, or whatever character, and then don't read in the other. Well, what about the yes case? So if we have a transition that looks like Q to Q prime as before, but here we're going to pop an X, then push a Y. Could I break this up into 2 transitions? Yeah, how would I do it?
You want to pop first and then push?
Correct. I want to pop first here because that's how the transition is going to operate anyway. So by popping first, I'm not breaking what the original PDA would have done. So I'm going to have 2 transitions yet again with Q double prime in the middle. Read on the first, don't read on the second. Pop on the first and no push. No pop on the second, push on the second. And that's how the transition works.
What
Yeah.
happens if you reverse the pop and push, or if you reverse the
Well,
median?
on which one? The first case or the second one?
The second case, if you reverse, let's say the
Mhm. Yeah, but that's not how the transition originally operated. The transition operates by popping first, then push, because we had this problem of if we pushed first, when we had push and a pop on the same transition, if we pushed on first, then the thing we wanted to pop is not at the top of the stack anymore. So we want to pop first, then push, because the thing, if we push first, then the thing that we wanted to pop is not at the top of the stack anymore. It's the thing that we just pushed. Right? Because it's a stack. Yeah.
Most of these examples that you drew for the no things?
No, so this one corresponds to that guy, and this one corresponds to this one. Yeah. Yeah. So if we have a push and a pop on the same transition, then we pop first, then push. If we don't do either, then we make it so that we push an arbitrary symbol, then pop the same thing. Oh, so we can convert any PDA into one that does exactly one of push or pop on every transition. That's pretty cool. There's one more question, but trust me, it's the last one. So, can every PDA be converted into one that, if it has an accepting computation, has another with the stack ending empty? So if we have a way of accepting in the original PDA, could I make another PDA that not only has the same accepting computation, but another one possibly where the stack ends empty? Yeah, so what do we do here? Correct. So, but what place should I do this popping of symbols in order to get the stack empty? How many final states do we have? Exactly one. So in the single final state, what are we going to do? We're going to have transitions that don't read and pop every symbol in the alphabet. So the PDA can, it doesn't have to, but it can empty the stack contents. So it just repeatedly stays in this state and pops all the symbols on the stack. It can, it doesn't have to, but it can. So the answer here is yes. So the idea is if we have the PDA construction like we had before, where we had these triple epsilon transitions in to go to this new final state, what we're going to do is we're going to add a self loop on that final state that doesn't read, pops an A, and pushes nothing for all characters in the stack alphabet. So I'm not saying that the stack has to end empty, but now if it accepted before, it can now accept with the stack empty. That's all I'm saying. Okay? Any questions? So let's think about how we're going to convert this arbitrary, now modified PDA into a valid CFG that has the same language. Well, let's think about what has to happen. What is the language of this PDA in terms of the states? Well, it's all the strings that take the PDA from the start state to where? To that single final state. Well, if I somehow knew in the middle how to get from this arbitrary state to this arbitrary other state, could I combine them so that I know how to get from the start state to the single final state. It seems like a logical process. If you know these subproblems, how do you make the entire problem work? So that's what we're going to do here. Well, what we're going to do is we're going to analyze what happened with the stack in a particular computation. So what happened with the stack means let's look at the stack height over time. So let's look at a arbitrary computation. So this bottom axis is time, and this vertical axis is stack height. And I want to see what happens over time in this modified PDA. Well, what does the stack always start with? 0 height. Okay, so that's helpful. In this modified PDA, what could the stack end as? Also empty. Yeah, so it may end empty, but it doesn't have to. But we're going to allow it to go to empty because it can. Could it go to empty in the middle of the computation? Yeah, we never restricted the PDA, so it can't go to empty in the middle. So it may hit 0 several times throughout. Okay? What does the first transition have to do? Push. Could it stay flat with the flat stack height? No, that corresponds to either doing both push or pop or neither. But we just eliminated those. So the first transition must push. And it may go up and down, and then let's say it hits 0 there, then it comes back up maybe, comes back down, does all these wild and crazy things, and then eventually comes down to 0. Okay? So this may be an arbitrary computation. I'm not saying that this is the only computation, I'm saying that this is one of them. So let's see. Let's look at this a little bit more detail. So I'm going to zoom in on this part right there. So let's see. So this is that very first push, just a little larger, and there's stuff in the middle, and then it came back to 0 way over here. Is there something that I can figure out about those two transitions? And I'm going to assume it never touched 0 in between. It has to be the same symbol that's involved. It pushed some symbol. Well, it never hit 0, as I said, during the middle, but then it came back down to 0, so it must have popped the exact same symbol. So if this pushes X, this pops X. Okay? Well, that's a subproblem. So if I know how to get from these two, to get from that middle state to that, I guess the third state, then I know how to get from the first state to the fourth state. And then by induction, I can go all the way from the first state to the final state. And then therefore I have the strings that I want. So now we need a way of representing the subproblem. And the way we're going to do that is with variables. So the variables that we're going to generate are all pairs of states that take me from that first state to the second state, but with an additional property that the stack height didn't change, didn't go below the what it started as. So it was empty stack to empty stack. So create variables A sub PQ, where P and Q are states of the PDA. So this is the subproblem that I have. What should be the start variable here?
Is it X because it's pushing X, right?
I should say what these variables are going to represent. So APQ will generate all strings that go from state P to state Q, empty stack to empty stack. So it's like the situation right above. The first state and the fourth state, that's from empty stack to empty stack. But as well as the second and third states in the middle, where the subproblem is. That's empty stack according to them to empty stack, because I never look at what the stack contents of that first push symbol is until I come all the way over here. And so therefore, it to them means empty stack to empty stack.
It's like a reference point at that point.
Yeah, yeah. It's like a reference point. So so what do you think the start variable would be is? Well, what is the language of the grammar? It's the things that can be generated from the start variable. What are the strings that the PDA generates, can recognize? It's from the start state to what state? To that single final state. So what do you think the start variable is? A sub the start state, Q0, to the final state. So it's A sub Q0, and I'm going to call it QF for the final state. So remember, so what does this start variable mean? It means all the strings that take me from Q0 to QF, empty stack to empty stack. You see why we wanted a single final state here? Because now I can reference all the strings in one variable here instead of having multiple variables. That's why I want a single final state. Any questions so far?
So
Yeah.
what was the in that diagram you have
Mhm.
above,
Mhm.
each time it comes back down to where the stack is empty.
Mhm.
I thought so. The one at the very end is the final state, but I didn't think the ones in the middle were final.
Correct, and we're going to handle that. Yep. We'll see how to handle if it happens to hit 0. Then if we know those two subproblems, how do you put them together? So we'll see that. Yeah. But the start variable is all the things that take me from Q0 to QF.
So the reason why the start variable is A of Q0 and QF is it just gives you all strings from the beginning to the end of the stack.
Yeah, because that's how we define the PDA. It's the things that take me from the start state to the final state. Mhm. Other questions? Okay, well, I told you what the variables should be, but we haven't really worked with them and made them so that that's what they really can actually generate. We made the start variable, and we know what the alphabet is. What thing have I forgotten to define? We got variables, got alphabet, start variable, and we didn't do the roles. Well, let's see. How are we going to do the roles? Well, we got to look at all pairs of states and work with what they could possibly generate. Well, let's start off with a really easy case. I may not know what an arbitrary pair of states is going to do, but could I reason about what the same state is going to do? So I'm thinking A sub PP is going to generate all strings from state P to state P with the same stack height. So there may be many ways I can go from the same state back to itself with the same stack height, but what's one way I could do that? Exactly, the empty string. If I want to go from myself to myself with the same stack height, an easy way is do nothing. And there's actually another reason why it is the empty string, but I'll show you that in a bit. But it seems intuitive that if I don't do any transitions at all, then the string I currently have is the empty string. So this is for all states P. So that gets us part of the way there. Well, now we got to reason about if it happens to hit 0 stack height in the middle, which it certainly can, like in my drawing earlier, it certainly can. So let's see what would happen here. So let's say we have that same diagram again, but now I'm just going to only make it come down to 0 one time. And let's say at the beginning it's state P. It doesn't have to be the start state, but this is just in general. Let's say it's P at the beginning, Q at the end is my destination, and R is the state that it happens to hit 0 at. Well, suppose I know the two subproblems, how to get from P to R, any string from P to R, and any string from R to Q. So what represents the strings that take me from P to R with the same stack height? APR. This is not tax season. All right. How do I get from R to Q with the same stack height? ARQ. Oh, if I know those two subproblems, do I know a way to get from P to Q with the same stack height? Yeah, how do I do it? APQ generates what? APR, then what? Concatenation, right? Because it's the strings that PR can make concatenated with the things that RQ can make. Because the computation from R to Q follows what happened with P to R. So for all triples of states, because I don't know what the computation is going to do, so why not just include every possibility that may happen, all triples of states. Add rule, APQ makes APR, ARQ.
Do we have to specify that P precedes Q?
No. So this generation of rules is going to doesn't even look at the PDA at all. It just looks at the states. It's going to make ones that make absolutely no sense. Like for example, if P cannot reach Q, then APQ is going to generate nothing. And so therefore that variable is useless, but might as well include it anyway, just in case. I want to be algorithmic about this. Okay? So just because I don't know the structure of the PDA in terms of what states can reach what, then I might as well just include all possibilities. Just like for NFA to DFA, I might as well include all states. There's no reason not to, in general. Any questions about that? If I had just had these two rule types, what would the language of the grammar be? At best. Would I generate any characters? No, I wouldn't generate any characters. It tells us how to get from states to states, but it doesn't tell me anything. So now we got to incorporate the transitions, like in this picture, where one transition pushes a certain symbol, then we can reason about what happens on the other transition where it pops the same symbol. So here's the third rule type. So I'm going to bring down the diagram we had before because it's going to be helpful. And don't worry, this is the final rule type. So we know that if we have two transitions like this where it pushes a certain character, then if it never touches below that point, anywhere in between, then that last transition must pop the same symbol. Could I guarantee this in an arbitrary PDA where those two transitions are? Could I guarantee anything? Not necessarily. I can't guarantee anything. So I'm going to have to look at every transition that pops a certain symbol corresponding with every transition that pops the same symbol. Did I say pops twice? Yeah. Every transition that pushes a certain symbol paired with every transition that pops the same symbol. Because there's no reason to look at two transitions where they push and pop different symbols. So I don't know if any of these states are going to be the same. They may all be different. So let's say that P is my source and Q is my destination. Well, the place I get to after the transitions in the middle, they may be the same state, they may be completely different states. But let's just say in general that they're different states. And let's say that there are an S. So here, I'm assuming I know how to get from R to S. What strings can I represent here that go from R to S with the same stack height? ARS. Well, I didn't say anything about what the transitions that push and pop that same symbol are going to read. So let's say in general that this one on the left that pushes reads an reads an A, and then the one on the right reads a B. In general, they may both be the empty string, but I'm going to have this be in general in case maybe they're not empty, but they could be empty. Well, could I describe APQ in terms of ARS and potentially other things? Well, let's see. How do I get from P to R? What do I read to get there? No, from P to R.
X, you push X.
But what am I reading though? Because remember, the grammar doesn't have a notion of it's not a, The PDA is something that has something to do with the stack, but the grammar that we're going to generate doesn't have anything to do with the stack. So we're not going to actually touch the stack in terms of generating characters from the stack, but we're matching transitions based on what things happened with the stack. Okay, well, what did I read along the way from P to R? Is the symbol A. How do I get from R to S? Well, there may be many ways, but I know it's something that ARS could generate. I don't know what it is, but it's something that ARS can generate. And then how do I get from S to Q? Read a B. So I'm going to add this rule for all PQRS are states, and having valid push pop transitions as above. I could dive into the formal semantics, but it's not necessary here. So let's try to recap what we're trying to do. I want to figure out how to get from the start state to that single final state. Well, I know that since we modified the PDA, every transition is going to have the stack height change by going up by 1 or down by 1. Every single one. It's never going to be flat. So if I know where it happens to hit the same stack height, the first one must have pushed and the last one must have popped. And so I can relate them by the third set of rules. But if I somehow know the whole subproblem where it happens to hit 0, then I can relate them via concatenation. But think about what that third rule is going to do. So I'm going to now talk about why we have the first set of rules. So if we look at this first part where it comes up and then comes down, and so we can see that the third set of rules is going to handle that first push and that very last pop, assuming it never hits 0 in the middle. Well, since it never hits 0 anywhere in the middle, then we can inductively use the same reasoning here. And then we can use this. Maybe it was this one. And then we have those two. But now consider this. If we're doing this reasoning over and over, then we apply it again here, then we come up again, and then one more time. So I'm going to match that push with that pop. But what happened when I got to this peak? Am I at the very same state on both sides? I'm at the same state. How do I get from the same state to the same state with the same stack height? Or what's one way? The empty string. So it's the concatenation of what I read along the way up and then on the way down. And so solving those two subproblems with the empty string in the middle guarantees I did this correctly, because it's just the concatenation of what I did on every transition. So that's why we have the first set of rules, so that when I eventually solve all these recursive subproblems, the base case is the empty string, because that represents coming to this peak because I'm at the same state on both sides, if I look at it going up on both sides of the hill, I guess. Okay? Any questions on why we did these three sets of rules?
Can we articulate all the rules one by one right now? Just walk through them.
Yeah, sure. So let's recap. I'll do a little example too. So first set of rules is for every single state in this modified PDA, have a rule A sub that state to that state makes the empty string. So that's just brute force elimination of, enumeration of those rules. Then for all triplets of states PQR, then I'm going to spit out the rule APQ makes APR AERQ. So the key here for this set of rules is that the first index of the one on the left side matches with the first index of the first variable, and the second index of the variable on the left matches with the second index on the second variable, and the ones in the middle match. That's the key. But I'm not looking at the PDA here. I'm just brute force generating all n cubed rules if there are n states. Okay? So once we do that, then we're going to look at every transition, every pair of transitions that push a certain symbol and the other one pops the same symbol. So there's no point in looking at transitions that do different things in terms of their stack. Once we have those two transitions, then I'm going to look at what states I went to in the middle, so the end of the push transition and the start of the pop transition. And then that's going to be my ARS. And then the other two states are going to be my APQ. And then put whatever I read on the first one with whatever I read on the second, and then just make that roll. Okay, I'm going to do an example, I promise.
I think I kind of lost it. Why are we doing all these steps?
Yeah. So what I'm trying to do is I'm trying to match what the PDA, the modified PDA, was going to do. Since we ended at the same stack height as when we started, 0 stack height, then the pushes with the pops are going to have to match. But then in order to match that first push with that last pop, I got to solve all the subproblems in between. So that's why.
So we won't know anything until we get to the tip, and then we can start building it backwards. Because we're using induction to get to the point, summit, and then after that we're coming back down.
Oh, no, you're doing induction on both sides.
Well, yeah, but then you find the point where, it hits and it starts going back down on both. That's where.
Yeah. Well, the grammar's going to handle that because it's generating both characters on both sides at the same time. Okay. Because it's making A and B on both sides. So it's in a sense is inductively already doing both sides for you. So it's like the 0S1. It's already making the 0 and 1 on both sides.
So then we just have to make, in this example, a rule for ARS, and then you can keep going.
Yeah. Mm-hmm.
Okay.
Yeah, so we're just implying it via induction. Yeah.
Similar to so at the peak,
Mm-hmm.
you're saying we're in the same state. Is that where exactly on the peak? Is it just
It's the very top node.
very top?
Yeah. The states along the way may be the same state, but I can guarantee the end of that last push with the start of that next pop must be the same state because I didn't execute any other transition. So it must be the same state.
Does that also mean that all of the pushes and the pops on both sides would have to match?
No, not necessarily. as long as it doesn't hit 0 in between. If you consider the cases where it doesn't hit 0 in between, then the pushes and pops have to match, yes. But if it happens to hit 0 in the middle, it may or may not match.
Oh, okay.
Yeah.
I understand.
Yeah, because I don't know the structure of the PDA beforehand, I don't know that. That's why we're doing this for every pair of transitions, just in case.
Okay.
Other questions? I'll do an example. All right, so let's do an example. So there's going to be at least n cubed plus n rolls for every PDA. So I'm not going to enumerate all possibilities. Do you think a computer can actually enumerate all those? Yeah. And so that's actually what the hint in problem set 3 is going to say. But let's do this. So now I got to make an example PDA. How about let's do the 0 to the n, 1 to the n one that we did before, to keep it simple-ish. If I make a mistake, please let me know. So here's the PDA that we talked about for 0 to the n, 1 to the n before. Is this PDA valid? In terms of what we did for modification?
Oh,
Only has one final state.
Well, it has a single final state, that's fine.
but it doesn't push and pop.
It doesn't only do one of push or pop on every transition. Like we actually only have one counterexample, which is this transition in the middle. So I didn't read on this guy, and I did neither push or pop on that transition. So what can I do to modify it?
Push something.
To push something to some new state, and then pop that happens to be the same symbol. So how about just for fun, let's pop that. Let's push and pop that special symbol, the $sign. So let's push on the $sign. It doesn't matter what it is. So let's call this Q4, for example. And then let's pop off this same character. Is this PDA now valid?
Yeah.
Sure. Well, we have one final state, and every transition does exactly one of push or pop. What was something else that we needed to do?
You have to pop your
Well, every stack symbol, yes. Yeah, so here I can actually guarantee that the PDA will end empty, but could I guarantee that in general? No. So I'm going to add on that final state self loops that pop off all of the stack characters. Well, the only things that touch the stack here are 0 and the $sign. Because we never put 1 on the stack, there's no reason to include it. So I'm going to have a transition where it pops a 0 and pushes nothing, and a transition that pops off the $sign and pushes nothing. This is the guarantee that there's a way to empty the stack.
Would it have been wrong to put that new final state with the triple epsilon transition into the self loop, or
You should, but for time reasons, I'm not doing that. But
You can't though, because it has to.
what's that?
Oh, you're saying.
Yeah, so he was asking, why didn't I make a new final state with a triple epsilon transition to a new final state? Well, there's no reason to here because we only need a single final state, and I'm popping everything off anyway. But the other problem is with that triple epsilon transition, now I need another state to handle that. Yeah.
What's an example of one of these that if you don't add that rule doesn't end empty? I just don't understand how it would. If it had an accepting computation, it just wouldn't end empty.
That's one.
But how would you get to the final state? You wouldn't. Right?
Yeah, well, if I push on the $sign, do the 0 thing,
Oh, and then you can
push, then pop $sign, then pop off all the zeros, then I can just immediately go over.
and you don't have to.
Yeah. So, yeah, in this example, I can guarantee once I enter Q3 gets final, but in general, I can't guarantee that. So I'm doing this just in case it happens to not be. Other questions?
So we always have to handle all the cases.
Yes. Yeah, you need to modify the PDA first. Yes. Okay. So let's enumerate 3 of each of the rule types. So there are 3 rule types, and let's do 3 each. So for the first one, can you give me an example of a rule type?
Oh,
A Q0, Q0 makes Q0, Q0 makes empty, yeah. So a Q0, Q0 makes empty. Another one, a Q2, Q2 makes empty. And a, I don't know, Q4, Q4 makes empty. And of course, there's going to be more. But I'm just going to enumerate 3 of each rule type to try to get some practice with this. So there are 5 states here. In the first one, I do it for every single state. So that means I'll have 5 rules. The second one, I have 5 states. How many rules am I going to generate? For all P, Q, R, and Q. What's that? Yes, it's n cubed, so I'll generate 125 rules. Do you think I want to enumerate all those? No. But could a computer do it? Yes. So let's enumerate some of them. So let's say I wanted to know how to get from Q0 to Q3. What's one way that I could do it? There are many ways I can do it, but what's one way I can do it? Well, I know that there are 2 variables on the right side. Do I know anything about those 2 variables based off of the one on the left side? Yeah, I start with Q0 and I end with Q3. And what do I know about the 2 in the middle? They must be the same. Any choice? Q4, let's do that. That's perfectly fine. How about A sub Q2, Q0? Will the variable A Q2, Q0, would that make anything in this PDA? No, because there's no way to get from Q2 to Q0, but might as well include it anyway. So I know that there are 2 variables again. The first one starts off with Q2 and ends with Q0. Any choice of what happens in the middle? Q1, let's say. So if I happen to know how to get from 2 to 1 and 1 to 0, then I know how to get from 2 to 0. Mm-hmm.
For the first one, could you say A Q0 Q3 is like A Q0 Q3 A Q3 Q3?
Yes. No, you include that because you need to have A Q3 Q3 in order to get the empty string. Yeah, those are actually the most necessary ones. So, other questions? Yeah.
So it's just one of the necessary combinations.
Yes. Mm-hmm. Yeah, you got to somehow get down to the empty string in order to make the variables disappear.
And you said that second one's a hypothetical rule, right?
Yeah, I'm including this rule no matter what. I'm not even going to look at the transitions.
Okay.
Yeah.
So in general, is AQ2 to Q0 the same thing as AQ0 to Q3?
No, because those are the, in this example, Q0 to Q2 is going to make something non-empty, but 2 to 0 is going to be totally empty. And even if the PDA represented a strongly connected graph, that doesn't necessarily mean the same thing because I may have an asymmetric what you read on each transition in both directions. Yeah. So if I happen to have a transition for from 2 to 0, let's say, on whatever, then that is going to be totally different than what 0 goes to 2 because it's not necessarily symmetric. Yeah.
So adding to her question, AQ3, Q3 would be both in group 1 and
Well, no, yes, yeah. So every variable where the states are the same is going to have at least two ways,
Okay, so-
at least two rules.
So we would add AQ3Q3 goes to AQ3Q3 AQ3.
Yes. Even totally nonsense ones. Yes. Other questions? Okay, so I think that's good for that example. Let's do one of this of the third type because it takes a little longer. So let's pick two transitions, one that pushes some symbol and another one that pops the same symbol. Any choice.
Q0, Q1.
Okay, so how about the 0 to 1 transition where we push on the dollar sign, and 2 to 3 where we pop the dollar sign off? So I'm going to rewrite these transitions down here in a convenient format. So this is going to pop the dollar sign off, and this one is going to push it on. Okay? Let's see. What is my R and S here? Q1 and Q2. If I know how to get from 1 to 2, then I certainly know how to get from 0 to 3. So what I kind of like doing is I like writing down what R is, what S is, what P is, and what Q is. So R in this case is Q1, S is Q2, P is Q0, and Q is Q3. So then now what I can do is I can just plug in the associated values that I need. Well, the rule says APQ. Well, here in this case it's AQ0, Q3. Well, what thing did I read on the first transition? Nothing. So my A is going to be empty. So it's empty. I'm not going to put it. What is my ARS? Well, I look at my handy chart. It says Q1, Q2. So AQ1, Q2. How do I get from 2 to 3? What do I read on the way? Nothing. And so that's the rule that I add. Okay? So if I know what things 1 to 2 will make, then certainly I know what 0 to 3 makes. Because to get from 0 to 1, I generated nothing. Then whatever 1 to 2 makes, then it generates nothing from 2 to 3. So all it is just solving subproblems. If you know how to solve the subproblem, then I can solve the general case. Any questions about that?
So it's kind of like dynamic programming.
Yeah, it's all dynamic programming. Yeah.
And since we're always putting in like a special symbol, it's going to be like the A and B. It's always going to be like epsilon, or it's not going to be there.
No, not every PDA is going to do that special symbol push at the beginning. It just happens that that one pushes a special symbol, but it's not necessarily characteristic. I know every transition. Actually, that's not true either. I was going to say that every first transition is going to push something, but certainly I may have a PDA where every transition pops and doesn't push. Yeah.
Would there be a rule 3 that would be something like, AQ1, Q2 would be 0,
Yes.
Q4, Q4?
Let's do one example. So let's do where it pushes a 0 and the other one where it pops a 0 on the 1 to 2 thing. So the first transition was Q1. So I'm going to depict it as a non-self loop, but it actually is a self loop here. So this first guy pushed on a 0, and then this last guy read a 1 and popped a 0. So as long as they push and pop the same symbol, we're good. So what is my rule going to look like then? Well, is A, P, Q? In this case, what is my P and Q? Q1 and Q2. And that's going to make, well, what did I read on the push transition? 0. And then what is my R and S? Q1 and Q2. So AP, no. Q1, Q2. And how did I get the pop transition? What did I read? 1. So then I add a 1.
So why is it Q1, Q1, not Q1, Q4, and Q4, Q2?
Well, Q4 was the thing that pushed and popped the dollar sign.
So you just kind of,
I look at every pair of transitions where they push and pop the same symbol. So I looked at these two transitions because they pushed, one pushes 0 and the other popped to 0. Okay? Any questions about these examples?
And we would do that for every combination.
Yeah, every pair of transitions that push and pop the same symbol. Yes?
Can you go back to your 3 example where you did AQ0, AQ3?
Yeah,
Where did it finish? Why isn't it AQ1, Q2, AQ2, Q3?
Because in order to solve the subproblem from 1 to 2, then I got to figure out how does 0 get to 1 and then from 2 to 3.
Okay.
So if I know how to get from 1 to 2, AQ1, Q2, then how do I get from 0 to 1? I don't read anything. So I don't read anything. Then I figure out how do I get from 1 to 2? Well, AQ1, Q2 is telling me what that is.
Right.
Then how do I get from 2 to 3? I generate nothing again.
Okay.
So it's just basically figuring out what do I read on each transition.
But so you don't need the AQ2, Q3 for that reason right there? Because the way it's written is you have AQ0, Q3 generates AQ1, Q2.
Yeah.
I thought the rule was, what's that rule?
It's in terms of what is actually read on the transitions.
Okay.
Okay? The first transition read nothing, and the second transition read nothing.
Okay.
And so therefore, I read nothing, generate whatever AQ1, Q2 could make, and then generate nothing again.
Okay.
wouldn't, okay, can you go back down to the bottom? Wouldn't that generate a loop though?
Yes.
So how would you ever get out of that? If
By
you just kept going
this is not the only rule corresponding to Q1, Q2. This is one of them. It's not the only one.
So it can pick any one that it wants.
Yeah, it's
That's
non-deterministic.
AQ1, Q2.
Mhm.
Okay.
Well, this looks like 0 to the n, 1 to the n, because
It
it
does,
generates the
yeah.
zeros and ones on both sides.
But then how would, so there would be another rule somewhere that would say
Yes.
Q1, Q2 is E.
Yeah, where because of that Q4 thing, it pushes and pops there. And then it'll have a Q1, Q2 with a Q4, Q4 in the middle, because we pushed and popped the dollar sign for Q4, and then therefore that would make epsilon.
That's what I don't understand though, is how would you get to that Q1, Q4? Would you have a rule that says?
Yeah, I look at every pair of transitions that pushes and pops the same symbol. And these two push and pop the same symbol. So that's a subproblem.
So there would be another rule for AQ1, Q2.
Yes, yeah. I said this is not the only rule for Q. This is one of them. Other questions? Yeah.
The rule be, what another rule be the AQ4, Q4?
Makes empty because that was in the first rule type. It's the base case. Other questions? All right, I think we've earned a 5-minute break, so let's take a 5-minute break.